Number 2, given a univariate linear model, h of x equals mx plus b. And the objective function equals that. If you present the training pattern x to y to update this model by stochastic gradient descent, what will be the updated values for m and b? Do you see that this is pretty much the same problem you did on the previous exam, except that I gave you no numbers. So instead of saying, hey, do it on a calculator, now I'm saying, do it in symbolic math. And to be clear, this is kind of what the class is all about. Yes, we're going to apply it to a whole bunch of different applications, but by the time you guys are taking the final, basically this question is going to be on the test, or maybe the one that was on the midterm one, or some variation of it, but I can only think of so many ways to ask the same question. Essentially, by the time you're done, you better get out of this class how to differentiate a darn neural net, because that's kind of what we do. So let's differentiate a neural net. We're going to start with, here's an equation. I'll just copy it down here for convenience. And this is our error function. One point that came up is some people got the error function, or the target function, also known as the objective function, mixed up with the blame that we assign to the output units in the neural net. That's not necessarily the same thing. This is the function we're trying to minimize. This is the overall objective function. And what we do is we differentiate it so we can descend the gradient of that function, meaning we're going to do backpropagation will compute how, if we change the weights, it will reduce our overall error function. From that, we'll derive what to assign as blame to the output units. This is not the blame on the output units. Okay. The derivative of that can be expressed as slash partial e slash partial w, where w is just some arbitrary weight that I haven't actually defined yet. So the partial derivative of this error function with respect to the partial derivative of w. That's what we're trying to get at. And that term, as it happens, is equal to slash partial w. I'm going to drop the e here and then put y sub I minus h of x sub I squared. And I'm doing this with a lot more detail than I expected on the test. It's okay if you didn't show every single step that I'm showing. This is, e is one thing. The partial of e with respect to the partial of w, what's that? That's the gradient, right? This is the answer to the question. If I change this weight, how will it affect my error? This is what we want to minimize, okay? So these are two totally different equations. It just happens this one's the derivative of that equation. Still with me on that? Okay, great. Well, now, just so that we're not getting confused about notation, do you see how I have partial e over partial w, and here I just have partial over partial w. There's nothing after the partial. Why? Because that's what this thing to the right is. I'm saying the partial of all that stuff to the right is the same as that. You see what I did with the notation there? Okay, so I'm just replacing that e with what e is equal to. I didn't do any math here. I've just substituted some stuff. I guess that is math. Okay, well, let's see if we can simplify any further. How do we get rid of this partial derivative thing there? We can't code up a partial derivative. There are ways of doing it, but we want to get rid of that partial derivative and resolve this to something we can evaluate numerically. How do we do that? The answer is the chain rule. Do you know the chain rule? It basically says, hey, the derivative of this thing is going to be, pull down that 2, and then multiply by the derivative of the inside. So that whole thing is going to be equal to, I'll just copy my symbol down there, 2 times y sub I minus h of x sub I. Some of you left it right there and forgot the important step of the chain rule is then and multiply by the derivative of the inside. Wait a minute. Times y sub I minus h of x sub I. That's what I meant to say. You see how I took that partial part and I got past the initial term, and now I've got another term in here that I'm taking the partial derivative of. So the chain rule didn't solve the problem in one shot. It got us one step closer to having the answer. Okay. Now, as it happens, this whole thing is equal to, we could just drop that y because it's not doing anything, right? I'm going to pull that minus out in front because I can, and change this to h of x sub I. And you don't even have to do it in this order. You can do it in any order you want. And some people didn't even do it in this way at all. But if you got the right answer, I'm happy with it. But all I did right here is I pulled the minus out in front and I dropped the y sub I. Why can't I drop the y sub I? Yeah, it is a label. If I change my weight, how does that affect that label? Doesn't at all. Therefore, it's garbage. It's a 0. Changing my weight has 0 effect on that label. Therefore, it's just dead weight in the function. I've omitted it. Now, how do we take the partial derivative with respect to w of a hypothesis of x? Short answer is you can't. So we have to expand h sub x. What is h sub x? We happen to have this equation right here. H of x is the same as mx plus b. So I'm going to expand that. And right here, mx x sub I plus b sub I. Is that what it was? Oh, it's just x plus b. Well, so then we have that. Now, there's a little bit of a terminology issue here. See, I was differentiating with respect to w. Why did I do that? I should have been differentiating with respect to m or b this whole time. Oops, sorry. By w, I meant m or b. Do I have to redo it? Will you forgive me if I just say, pretend all those w's are actually m's or b's or whatever I want them to be. Okay, so if that's the case, then what is the partial derivative with respect to m of mx plus b? It's x. Actually, it's x sub I in this particular case, if we want to be technical. And what is the partial derivative with respect to some weight of mx plus b if, excuse me, what is the partial derivative with respect to b of mx plus b? Right, so times 1. Can I just drop the times 1 without, you understand if I just back that out, right? Okay, so this one is the slash partial of e with respect to slash partial of m. And this one is the slash frac slash partial. I'm secretly teaching you with tech while I show you the answers here. Slash partial of b. And why did you put it on that end? Weird OpenOffice or LibreOffice, whatever you are. Okay, so I have differentiated my model with respect to m. It's this. And I've differentiated the error function with respect to m, and I've done it with respect to b. Now, how do we actually update m, and how do we actually update b? We say m is equal to m plus eta, which is that symbol I keep using for the learning rate. See, I said right here, use the learning rate of eta. Yes, eta looks like an N with a hanging down extra line. If you want to call it N, I don't care, but it's pronounced eta. I do care. You should learn your darn Greek letters if you're going to be grad students. Learn your Greek letters, that's eta. Times, now here's a little detail that kept coming up, and some of you aren't going to like me for it, but this partial derivative, what exactly does it say? It says if I make b a little bit bigger, how much a little bit bigger does it make the error, right? You see that this is the positive, this is the make it worse gradient, this is not the make it better gradient. So do I want to make my error function bigger or smaller? Smaller, therefore I don't add this gradient, I subtract it. Notice there's a minus sign in front of it. But that minus sign was part of the make it worse gradient. So in fact, if I'm going to add, then I need to only add this part of it, not including the minus sign. And or I could subtract it and include that minus sign if I want to, which is the same thing. That reduces to this. So there you go. It should have been like that. And b is equal to b plus eta. Let's do eta times this thing, not including the minus sign. There you go.
You drop the 2?
And yes, we can or not, depending on what we feel like it. It's totally okay to drop the 2 because eta is there anyway, and what's eta? Whatever the heck number we want it to be. Therefore, we could just make that number be twice as big. So yes, you can drop the 2, or you can not drop the 2, and I don't care which you did in your answer. Yes?
So I'm a little confused about the sign, because if we have d dm equals a negative number, isn't that saying that a positive change in n results in a negative change in error, which is good?
So, got to think about this for a minute. We should probably do an empirical test is the best way to answer your question. And because this model is so simple, I bet we could just do it really fast. Let's try it. Let us suppose that m is 1 and b is 0. And so we're basically doing the identity function. So we're saying x is equal to y. Say that's the case. Now let's suppose x is 1 for convenience, and y sub I is 1.1. So we're actually predicting a 1, because we're feeding in a 1 and the identity function predicts a 1, but we wanted a 1.1, so we're off by 0.1. We want to get a little, if our training method is correct, we should push the weights in such a manner that we make a slightly bigger prediction. With me? Okay. Well, let's say that's the case. Now, m, which was 1, is equal to 1 plus eta, some tiny amount, times y minus h of x. That's going to be 1.1 minus 1, so 0.1, times x sub I, 1, so 0.1. In other words, m is going to get a little bit bigger. I claim that if m gets a little bit bigger, that's going to make the identity function a little bit bigger, which is closer to what we said for y sub I, which was 1.1. So I claim I just passed the empirical test. Yeah, so somewhere between my empirical test and the intuition is whatever was confusing. And the answer is, yeah, this gradient is how to make the error worse. So I'm subtracting that gradient, which is the same as adding everything without that minus sign. All right, so this is the answer I really wanted. Now, About half of you gave exactly that answer, and good job, nailed it. A lot of you gave something else, and I had to judge how much you understood what was going on. I have this bleeding heart. I sat there figuring out what you guys were thinking for a long time, and in most cases I think I figured out what you were thinking, and in most cases I ended up talking myself into giving you way more points than you deserved, so you all got way more points than you deserved. But if on the final I just stick a test question you've seen before, I'm going to lose my my tolerance for error very quickly, because I expect you to learn from mistakes, right? So plan on seeing this question again and plan on me grading it like this. Did you get the answer exactly correct? No, wrong. Or yes, right. But I was, of course, more partial credit oriented because I'm human. Okay, there you go. But that's the answer I wanted for that one. Any questions?